Let us see what happens when atoms with different electronegativities combine to form a covalent bond. When two atoms with different electronegativities combine to form a covalent bond, the electron density between atoms is shared in such a way that it is displaced more towards the more electronegative atom. As a result, the more electronegative atom gets a partial negative charge, while the less electronegative atom gets a partial positive charge. The partial positive and negative charges on the dipole are indicated by the symbols delta plus and delta minus respectively. Therefore, in heteroatomic molecules in which the two atoms differ considerably in electronegativity, two electric poles develop. We say that the molecule has developed polarity. The covalent molecule with the two oppositely charged poles is called a dipole. For example, the dipole in hydrogen chloride is represented as shown here. Hence, the bond is called a polar covalent bond, and the molecule is called a polar covalent molecule. Examples of polar covalent molecules are hydrogen fluoride, hydrogen chloride, water, and nitrogen trifluoride. When atoms with the same electronegativity combine together to form a covalent bond, such a bond is said to be a non-polar covalent bond. Here, no polarity is developed in the molecule as the shared electron pair lies exactly between the bonded atoms. Molecules with non-polar covalent bonds are called non-polar covalent molecules. Examples of non-polar covalent molecules are hydrogen, fluorine, chlorine, oxygen, and nitrogen. Let us now move on to the concept of dipole moment. The polarity in a polar covalent molecule is expressed in terms of dipole moment. Dipole moment is defined as the product of the magnitude of the charge and the distance between the centers of the positive and the negative charge. Dipole moment is denoted by mu and is equal to the product of charge q in coulombs and distance of separation r in meters. Dipole moment is a vector quantity, which means it has both magnitude and direction. The unit for dipole moment is called dBi and is denoted by d. 1d is equal to 3.33564 into 10 to the power minus 30 coulomb-meter. Dipole moment indicates the degree of polarity in a molecule. Dipole moment is represented by a crossed arrow starting at the positive pole and pointing towards the negative pole. For example, the dipole moment of hydrogen chloride is represented as shown. The crossed arrow indicated above a Lewis structure indicates the direction of electron shift. In case of polyatomic molecules, the dipole moment depends on the individual dipole moments, called bond dipoles, and on the spatial arrangement of various bonds in the molecule. The net dipole moment is the vector sum of the dipole moments of all the bonds present in the molecule. Let us calculate the dipole moment of some molecules. Consider the beryllium chloride molecule. It is a linear molecule with a bond angle of 180 degrees. In the beryllium chloride molecule, two beryllium chlorine bonds are present in opposite directions. As chlorine is more electronegative, the shared electron pair moves closer to chlorine, so that it acquires a partial negative charge while beryllium acquires a partial positive charge. The bond dipole between the two beryllium and chlorine bonds is represented as shown. As the two equal bond dipoles are in opposite directions, their vector sum is 0. So, the net dipole moment is 0. Let us take another example. A water molecule. In a water molecule, there are two oxygen-hydrogen bonds. It is angular in shape with a bond angle of 104.5 degrees. Oxygen being more electronegative, the shared electron pair between oxygen and hydrogen stands very close to the oxygen atom. So, the oxygen atom gets a partial negative charge, while hydrogen gets a partial positive charge. The bond dipole lies towards the oxygen atom. The net dipole moment is the resultant of the two bond dipoles of oxygen and hydrogen bonds. The net dipole moment, mu, in water is 1.85 dBi. Now let us take the example of a boron trichloride molecule. In this molecule, 3 boron-chlorine bonds are present at an angle of 120 degrees to one another. The resultant dipole moment of any two boron-chlorine bonds is equal and opposite to the third boron-chlorine bond dipole, as shown here. Hence, the net dipole moment is equal to 0. Let us take the carbon tetrachloride molecule. As the resultant bond dipoles, as shown here, are equal and in opposite directions, they get cancelled, and the net dipole moment of the molecule is equal to 0. It is really interesting to know that different molecules with the same geometry or shape may have different dipole moments. Let us consider ammonia and nitrogen trifluoride molecules. Both of them have pyramidal shapes with a lone pair of electrons on each nitrogen atom. But the dipole moment of ammonia is greater than that of nitrogen trifluoride, though fluorine is more electronegative than nitrogen. There is an explanation. The dipole moment of ammonia is 4.9 into 10 to the power of minus 30 coulomb-meter, while that of nitrogen trifluoride is 0.8 into 10 to the power of minus 30. In the ammonia molecule, there is a lone pair of electrons on the nitrogen atom and 3 nitrogen-hydrogen bonds present in the molecule. The bond dipole is directed towards nitrogen, as it is more electronegative than hydrogen. The resultant dipole moment is in the same direction of the orbital dipole due to the lone pair of electrons on the nitrogen atom. The nitrogen trifluoride molecule has a lone pair of electrons on the nitrogen atom and 3 nitrogen-fluorine bonds. Since fluorine is more electronegative than nitrogen, the bond dipole is towards the fluorine. The resultant dipole moment is in the opposite direction of the orbital dipole due to the lone pair of electrons on the nitrogen atom. Hence, the dipole moment of ammonia is more than that of nitrogen trifluoride. Hence, we can conclude from the polarity of bonds and dipole moment that a covalent bond has a partially ionic character. Based on the Fajans rule, we can say that ionic bonds also have some partial covalent character. To know about the partial covalent character in an ionic bond, we should know Fajans' rules. According to Fajans' rule, when two oppositely charged ions approach each other, the cation attracts the outermost electrons of the anion. Due to this, the electron cloud of the anion gets distorted. This is called polarization. The tendency of the anion to get polarized by the cation is called polarizability. As a result of polarization and polarizability, the positive and negative charges decrease on the cation and anion. This means that the electronic charge becomes more concentrated between the two bonded atoms and is responsible for the development of a covalent character in ionic compounds. If the extent of polarization is small, then the bond is more ionic in nature. If the extent of polarization is more, then the bond is more covalent in nature. The smaller the size of the cation, the greater is the covalent character of an ionic bond. For example, lithium chloride is more covalent than sodium chloride because the size of the lithium cation is less than that of the sodium cation. The smaller cation has a higher electron density, and hence it can distort the electron cloud of the anion easily. The larger the size of anion, the greater is the covalent character of the ionic bond. For example, sodium iodide is more covalent than sodium chloride because the iodide ion is larger than the chloride ion. For an anion of large size, the electron cloud on it is loosely bound to it, and hence can be easily distorted by the cation. The larger the charge on the cation or anion, the greater is the covalent character of the ionic bond. For example, stannic chloride is more covalent than stannous chloride because the charge on tin in stannic chloride is 4, while it is 2 on stannous chloride. On the other hand, sodium sulfide is more covalent in nature than sodium chloride because the charge on the sulfide ion is greater than the charge on the chloride ion. Cations of the same size and charge, the cation with an inert gas configuration forms compounds with more ionic character. The cation with pseudo-inert gas configuration, that is, with 18 electrons in the outermost shell, forms compounds with more covalent character. For example, copper 1 chloride is more covalent in nature as compared to sodium chloride. Copper ion with pseudo-inert gas configuration has an electronic configuration of 2, 8 and 18. Sodium ion with inert gas configuration has an electronic configuration of 2, 8. Lewis' concept does not explain the shapes of molecules. In 1940, this drawback led Sedgwick and Powell to come up with a theory to determine the shape of a molecule. The shape of the molecule is based on the number, type, or extent of repulsions between electron pairs present in the valence shell around the central atom respectively. This theory is named as valence shell electron pair repulsion theory, or the VSEPR theory. It was further developed and redefined by Gillespie and Nyholm in 1957. The valence electron pairs surrounding the central atom in a molecule mutually repel with each other. Thus, these electron pairs surrounding the central atom arrange themselves in space in such a way to minimize the repulsions, giving the molecule a definite geometry. The molecules in which the central atom is surrounded with only bond pairs, then it is said to possess definite geometry, as in case of BF3. As the electron pair is a negatively charged cloud, the bonded atoms move apart to minimize repulsions between the electron pairs. To minimize the repulsion, the distance between the atoms has to be maximum. To attain the maximum distance between the bonded atoms, imagine the valence shell to be a sphere and the electron pairs located on its surface at maximum distance from each other. The shape of a molecule depends upon the number of valence electron pairs and their arrangement around the central atom. The geometry of a molecule, in which the central atom does not have a lone pair of electrons, will be regular without any distortion. For example, the shape of a molecule with two bonded electron pairs around the central atom will be linear, with a bond angle of 180 degrees. The shape of a molecule with three bonded electron pairs around the central atom will be trigonal planar, with a bond angle of 120 degrees, and so on. In a methane molecule, 4 hydrogen atoms are bonded to one central carbon atom. Since the electron pairs have the same charge, they repel each other and try to stay as far away from each other as possible. As a result, all the 4 hydrogen atoms arrange at 4 corners of a tetrahedron, lying at equal distances away from each other. Hence, methane has tetrahedral shape. In the methane tetrahedron, the bond angle is 109 degrees 28 minutes. However, the geometry of the molecules gets distorted due to the presence of lone pair of electrons. Unlike bonded pairs that are shared between two atoms, the lone pairs of electrons are localized on the central atom. Due to this, they occupy more space, which results in greater repulsion. Thus, the geometry of the molecules with lone pair of electrons differ from the expected or regular geometry of the molecules having only bond pairs. In a molecule, the repulsion between lone pairs of electrons is always maximum. Thus, we can say that the repulsion between two lone pairs of electrons is more than that of a lone pair bond pair, which is greater than that of two bonded pairs. Assume a multiple bond to be a single electron pair. Therefore, the presence of multiple bonds will not affect the shape of a molecule. Now, let's analyze the shapes of some molecules with reference to their valence electron pairs. In ammonia, the central nitrogen atom has 3 bond pairs of electrons and 1 lone pair of electrons. The ideal geometry of the molecule with 4 pairs of electrons would be tetrahedral. However, the lone pair of electrons repulses the NH bonded electron pairs, thus reducing their bond angle to 107 degrees and giving the molecule a pyramidal shape. In a water molecule, the central oxygen atom has 4 bonded pair of electrons and 2 lone pair of electrons. We have seen that repulsion between lone pair, and lone pair bond pair is more than bond pair. Thus, the 2 lone pairs on central oxygen atom makes the molecule to distort from its regular geometry to bend or V-shape, making a bond angle of 104.5 degrees. A sulfur tetrafluoride molecule is seesaw-shaped as its bond angles are at an angle of 101 and 173 degrees. Due to the lone pair of electrons present on its central atom. The chlorine trifluoride molecule is T-shaped and its bond angle is 87 degrees and 40 minutes, and the molecule shape is distorted due to the 2 lone pair of electrons on central chlorine atom. In a molecule of bromine pentafluoride, the central atom bromine has 5 bonded pair of electrons and 1 lone pair of electrons. Therefore, the geometry of the molecule is distorted, octahedral or square pyramidal. It is due to the presence of a lone pair of electrons on central bromine atom. In a molecule of xenon tetrafluoride, the central xenon atom is surrounded by 4 bonded pairs of electrons and 2 lone pairs of electrons. The geometry of the molecule is distorted to square planar from the regular octahedral geometry. It is due to the presence of 2 lone pairs of electrons on its central xenon atom. Although Lewis's approach to chemical bonding helps us to write the structure of molecules, it suffers from certain drawbacks. These drawbacks are: it fails to explain the formation of a chemical bond. It does not give the reason for the difference in bond dissociation energy and bond lengths in molecules like hydrogen and fluorine, although in both the cases a single covalent bond is formed. It also fails to give any idea about the shapes of the polyatomic molecules. The VSEPR theory, on the other hand, gives the geometry of the simple molecules but fails to explain their formation. To overcome these limitations, the valence bond theory and the molecular orbital theory, which are based on quantum mechanics, are introduced. The valence bond theory was introduced by Heitler and London and was developed further by Pauling and Slater. It explains the formation of covalent bonds. According to this theory, a covalent bond is formed when a pure valence atomic orbital of one atom overlaps with pure valence atomic orbital of another atom. Each of the overlapping orbitals contains the unpaired electron of opposite spin. The electron pair is shared by both the atoms. The strongest bond is formed when the orbitals of the 2 atoms overlap to the maximum extent. Let's explain the formation of hydrogen molecule on the basis of this theory. Consider 2 hydrogen atoms, A and B, approaching each other. Let us label their nuclei as Na and Nb and the electrons present in them as Ea and Eb. Now, as these 2 atoms come closer, forces of attraction as well as repulsion begin to operate. The force of attraction arises between the nucleus of one atom and its own electron, that is, between Na and Ea, and between Nb and Eb, and the nucleus of one atom and electron of another atom, that is, between Na and Eb, and between Nb and Ea. Simultaneously, repulsive forces also arise between the two electrons Ea and Eb, and the two nuclei Na and Nb. Experimentally, it is found that the magnitude of the new attractive forces is more than that of the new repulsive forces. As a result, the potential energy decreases as the two hydrogen atoms approach each other. Ultimately, a stage is reached where the nuclei remains at an optimum distance, such that the net force of attraction balances the net force of repulsion. At this stage, the system acquires minimum energy, and the two hydrogen atoms are said to be bonded to form a stable molecule. If we try to bring these atoms still closer, then the repulsive forces start overpowering the attractive forces. Consequently, energy of the system increases, causing instability to the system. As energy is released during the formation of the bond between the two hydrogen atoms, we can say that the hydrogen molecule is more stable than the isolated two hydrogen atoms. The energy so released is called the bond enthalpy, which corresponds to the minimum as shown in the figure. It is important to note that the same amount of energy is required to dissociate one mole of hydrogen molecule. Another example is the formation of a hydrogen chloride molecule. Here, when hydrogen atom approaches chlorine atom, a bond is formed due to the overlapping of s and p orbitals. The overlap can be positive, negative, or zero depending on the properties of the respective overlapping orbitals. Based on the overlapping of orbitals, two types of covalent bonds are formed. These are known as sigma and pi bonds. Sigma bonds are formed by the end-to-end overlap of atomic orbitals along the internuclear axis, known as a head-on or axial overlap. There are three types of head-on overlaps that form sigma bonds. They are SS overlap, SP overlap, and PP overlap. SS overlapping takes place when two half-filled s orbitals overlap along the internuclear axis. SP overlapping takes place when the half-filled s orbital of one atom overlapped with the half-filled p orbital of another atom along the internuclear axis. PP overlapping takes place between two half-filled p orbitals of two atoms along the internuclear axis. A pi bond is formed when atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The pi orbitals formed due to the sidewise overlap consists of two saucer-type charged clouds above and below the plane of the participating atoms. Pi bonds can be formed in addition to a sigma bond between two atoms and are always present in molecules with multiple bonds. The overlapping of orbitals extends to a larger area in sigma bonds than pi bonds. Therefore, sigma bonds are stronger than pi bonds. The overlap criterion of orbitals applies equally to both diatomic molecules and polyatomic molecules. However, the valence bond theory fails to determine the actual shapes of the polyatomic molecules, such as methane, ammonia, and water, which are tetrahedral, pyramidal, and bent respectively. Let us explain the above limitation by considering methane molecule. In methane, the central atom carbon has the configuration of 1s2, 2s2, 2px1, 2py1. In its excited state, the configuration becomes 1s2, 2s1, 2px1, 2py1, 2pz1. The four atomic orbitals of carbon, each with an unpaired electron, overlaps with four singly occupied 1s orbitals of the hydrogen atoms to form 4 CH bonds. We know that p orbitals lie perpendicular to each other. Hence, the 3 CH bonds in methane molecule are expected to be oriented at 90 degrees to one another. The 2s and 1s orbitals of carbon and hydrogen can overlap in any direction, since they are spherically symmetrical. Thus, the direction of the fourth bond cannot be ascertained. This means that all the 4 CH bonds in methane are not identical. But experimentally it is observed that all the 4 bonds are exactly identical in all aspects and are oriented at a bond angle of 109.5 degrees. Similarly, valence bond theory cannot account for the correct bond angles in water and ammonia. While valence bond theory predicts to have a bond angle of 90 degrees in them, the experimental result suggests to have bond angles of 104.5 degrees and 107 degrees respectively. Thus, it can be seen that the valence bond theory fails to account for the actual shape of polyatomic molecules. During their research, scientists observed that some molecular structures found in nature could not be scientifically explained with the help of the existing understanding of atomic orbitals. Pauling introduced the concept of the hybridization of atomic orbitals to explain the existence of such molecules. During hybridization, atomic orbitals of slightly differing energies redistribute to form a new set of orbitals with equivalent energies. The number of hybridized orbitals formed is equal to the number of atomic orbitals participating in the process. These hybrid orbitals align themselves in space such that there is minimum repulsion between the electron pairs. Because of this, the bonds formed by hybrid orbitals are more stable as compared to those formed by pure atomic orbitals. The phenomenon of hybridization is observed in the atomic orbitals s, p and d. Their possible combinations are sp, sp2, sp3, sp3d and sp3d2. Now let's study each combination in detail. In sp hybridization, one s orbital combines with one p orbital to form 2 equivalent sp hybrid orbitals. The hybrid sp orbital shows 50% characteristics of the s orbital and 50% characteristics of the p orbital. The hybrid orbital has a large positive lobe and a very small negative lobe. The hybrid orbitals are oriented in opposite directions, forming an angle of 180 degrees with each other. During bond formation, they provide maximum overlapping areas, making the bonds stronger and giving the molecule its linear structure. Some compounds whose central atom displays sp hybridization are BeCl2 and C2H2. In sp2 hybridization, one s orbital combines with two p orbitals to form three equivalent sp2 hybrid orbitals. They have a trigonal planar arrangement, and the angle between two orbitals is 120 degrees. Some compounds whose central atom displays sp2 hybridization are BCl3 and C2H4. In sp3 hybridization, one s orbital combines with all the three p orbitals to form four equivalent sp3 hybrid orbitals. Each hybrid sp3 orbital displays 25% s orbital characteristics and 75% p orbital characteristics. They have a tetrahedral arrangement, and the angle between two orbitals is 109.5 degrees. Some compounds whose central atom displays sp3 hybridization are CH4 and C2H6. The hybridization of elements containing d orbitals leads to three distinct hybridized shapes formed by the mixing of s, p and d orbitals. They are dsp2, sp3d and sp3d2. Of these, we will study sp3d and sp3d2 hybrid orbitals closely. The energy of 3d orbitals is not only comparable to 3s and 3p, but also comparable to 4s and 4p. Therefore, the hybridization of d orbitals either involves the 3s, 3p and 3d orbitals, or the 3d, 4s and 4p orbitals. In sp3d hybridization, one s orbital, 3p orbitals and one d orbital combine to form 5 sp3d hybrid orbitals of equivalent energy. They have a trigonal bipyramidal arrangement, which leads to the formation of two different sets of angles between orbitals. Three of the hybrid orbitals lie in one plane, making an angle of 120 degrees with each other. This plane is called the equatorial plane, and the bonds formed by them are called equatorial bonds. The remaining two orbitals arrange themselves above and below the equatorial plane, forming an angle of 90 degrees with the orbitals on the equatorial plane. The bonds formed by these two orbitals are called axial bonds. The axial bonds are repulsed by the equatorial bonds, causing them to be longer and weaker than the equatorial bonds. Ultimately, this makes molecules with sp3d hybridization more reactive. The central atom, phosphorus, in the compound PCl5 displays sp3d hybridization. In sp3d2 hybridization, one s orbital, three p orbitals and two d orbitals combine to form 6 sp3d2 hybrid orbitals of equivalent energy. They have an octahedral arrangement and a bond angle of 90 degrees between the orbitals. The central atom, sulfur, in the compound SF6 displays sp3d2 hybridization. Thus, we can observe that the phenomenon of hybridization explains the characteristic geometrical shapes of polyatomic molecules. In an atom, electrons are present in orbitals of differing energy levels, such as 1s, 2s, 2p, and so on. They represent the probability of finding electrons around an atom. This observation led scientists F. Hunt and R. S. Millikan to develop the molecular orbital theory, which postulates that electrons in a molecule similarly exist in different orbitals, giving the probability of their presence around a molecule. However, for atomic orbitals to combine and form molecular orbitals, they must have similar energy levels and symmetrical molecular axes. This means that even though 2px of one atom has energy equal to 2py of another atom, they won't combine as they don't have the same symmetry. The number of molecular orbitals formed is equal to the number of atomic orbitals in the atoms forming the bond. Electron distribution in molecular orbitals takes place as per the off-Bohr principle and obeys Pauli's exclusion principle and Hund's rule. The electrons in an atom are influenced by only one nucleus, forming monocentric atomic orbitals. However, the electrons distributed in molecular orbitals are influenced by the nuclei of all the atoms forming the molecule, causing the formation of polycentric molecular orbitals. In an atom, the electrons present in the atomic orbitals are represented using the Schrödinger wave equation of wave mechanics by the wave function y, which gives the amplitude of the electron wave. However, the Schrödinger wave equation cannot be used for molecules, and hence a new method called the linear combination of atomic orbitals, LCAO, was developed. To understand this method, let's consider the hydrogen molecule made up of two hydrogen atoms, A and B. At ground state, each hydrogen atom has one electron in the 1s orbital. Let's represent their wave function as psi A and psi B. Now, there are two ways to add the wave functions. One is when these wave functions are in phase, either both plus or both minus. And the other is when the two wave functions are out of phase, one plus and the other minus. When the two electron waves are in phase, they form the bonding molecular orbitals. Here, the electron density is between the two nuclei. The electrons tend to hold the nuclei together, thus stabilizing the molecule. Therefore, we conclude that a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. When the two electron waves are out of phase, they form antibonding molecular orbitals. Here, the electron density between the two nuclei is reduced such that it is zero at the nodal plane. This leads to mutual repulsion of the electrons. As the energy of the mutual repulsion is more than the attraction between the electrons and the nuclei, the net orbital energy increases. Thus, the energy of the anti-bonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital is lowered than the parent orbitals. However, the total energy of the two molecular orbitals remains the same as that of the two original atomic orbitals. As we have learnt, molecular orbitals are obtained by combining the atomic orbitals of the atoms in a molecule. For example, in the hydrogen molecule, each atom has one electron in its 1s orbitals. These two 1s orbitals come together to form two molecular orbitals. One of these two molecular orbitals is formed due to the constructive interference of the two 1s wave functions, and the other is formed due to the destructive interference of the two 1s wave functions. The molecular orbital formed due to constructive interference is called a bonding molecular orbital, as the electrons belonging to it are placed between the two nuclei. This stabilizes the molecule. The molecular orbital formed due to destructive interference is called an anti-bonding or sigma star molecular orbital, as the electrons belonging to it are placed away from the region between the two nuclei. This increases their energy, thus making the molecule less stable. Just as in atoms, electrons in a molecule too first occupy lower energy levels. Thus, we find that the two electrons of the hydrogen molecule first occupy the sigma bonding molecular orbital. This lowers the overall energy of the molecule compared to the isolated hydrogen atoms. Molecular orbitals not only help us determine the stability of molecules such as hydrogen, they also help us understand why certain molecules such as the helium diatomic molecule do not exist in nature. You see, helium atom has two electrons in its 1s orbital. When two helium atoms come together to form a molecule, the 4 electrons would be distributed across both sigma bonding and sigma star anti-bonding molecular orbitals. The energy of the sigma bonding molecular orbital will be low. However, the energy of the sigma star anti-bonding molecular orbital will be considerably higher. Thus, the overall energy of a helium diatomic molecule will be the same as that of two helium atoms. So, there will be nothing holding them together. Hence, the helium diatomic molecule does not exist. 4 molecules formed by atoms containing more than 2 electrons. We will only consider the molecular orbitals formed by their valence shell and not the ones formed by their core orbitals to understand their stability. Now let's study the molecular orbitals formed in an oxygen diatomic molecule. Oxygen has the atomic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. When 2 oxygen atoms come together, their 1s2 atomic orbitals combine to form two molecular orbitals. Their electrons are concentrated along the bond axis. Hence, they are called sigma 1s bonding and sigma star 1s antibonding molecular orbitals. The two 2s orbitals combine to form sigma 2s bonding and sigma star 2s antibonding molecular orbitals. Two 2pz orbitals too combine head-on to form sigma 2p bonding and sigma star 2p antibonding molecular orbitals. However, the two 2px and 2py orbitals combine sideways to form a p orbital shaped bond with the electrons concentrated either above or below the bond axis. Hence, these molecular orbitals are called pi orbitals. The two px atomic orbitals combine to form pi x bonding and pi star x antibonding molecular orbitals, whereas the two py atomic orbitals combine to form pi y bonding and pi star y antibonding molecular orbitals. As the energies of the 2px and 2py atomic orbitals are the same, the energies of pi x bonding, pi y bonding molecular orbitals and pi x star antibonding, pi y star antibonding molecular orbitals are the same. Thus, the interaction between the valence shells of two oxygen atoms leads to the formation of 8 molecular orbitals: sigma 2s, sigma star 2s, sigma 2p, sigma star 2p, pi x, pi y, pi star x and pi star y. Due to the difference between 2s and 2p atomic orbitals, the resultant molecular orbitals sigma 2s and sigma star 2s lie below the other 6 orbitals. Due to the head-on bonding between 2pz atomic orbitals, the interaction between them is stronger than the 2px and 2py orbitals. As a result, the sigma 2p orbital lies below the pi x and pi y orbitals, and the sigma star 2p orbital lies above the pi star x and pi star y orbitals. While this sequence of molecular orbitals is accurate for molecules such as oxygen and fluorine, but not for other elements such as boron, carbon and nitrogen, the molecular orbital's energy sequence is slightly different. This is because of the interaction between the electrons of the 2s atomic orbitals of one atom with the electrons of the 2pz atomic orbitals of another atom due to their relatively similar energy levels. In these molecules, the energy level sequence is sigma 2s, followed by sigma star 2s, followed by pi x and pi y that are at the same energy levels, followed by sigma 2p, followed by pi star x, pi star y, and finally sigma star 2p. As we know, the number of bonds between a pair of atoms is called the bond order. In terms of molecular orbitals, to calculate the bond order, we assume that 2 electrons in a bonding molecular orbital form one bond, and that 2 electrons in antibonding molecular orbitals cancel the effect of one bond. Thus, we can calculate the bond order in an oxygen molecule using the formula bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding molecular orbitals divided by 2. Now, in oxygen, the number of electrons in the bonding orbitals is 8, and the number of electrons in the anti-bonding orbitals is 4. So, adding these values to the equation, we get the bond order as 2. As we know, when electrons in an atom or molecule are paired, as in nitrogen, they form a dimagnetic atom or molecule. And when the electrons in an atom or molecule are not paired, as in oxygen, they form a paramagnetic atom or molecule. In this way, the molecular orbital model helps us understand the structure and properties of molecules. Let us start with the hydrogen molecule, which is formed by the combination of two hydrogen atoms. You know that a hydrogen atom has just one electron, and it is placed in the 1s orbital. So, a hydrogen molecule will have two electrons that are present in the sigma 1s molecular orbital. The electronic configuration of a hydrogen molecule is sigma 1s2. Let us calculate the bond order of hydrogen molecule. As the number of electrons present in the bonding orbital is 2, and as no electrons are present in anti-bonding orbitals, the bond order is equal to 2 minus 0 divided by 2, which is equal to 1. This shows that there exists a single covalent bond between two hydrogen atoms. The hydrogen molecule is dimagnetic in nature, as no unpaired electrons are present in its molecular orbitals. Now let us discuss the bonding in a helium molecule. A helium atom has two electrons in its 1s orbital. Hence, the number of electrons in a helium molecule is equal to 4. These electrons occupy the sigma 1s and sigma star 1s molecular orbitals. Hence, the electronic configuration of a helium molecule is sigma 1s2, sigma star 1s2. Now, from the electronic configuration of helium, we can easily derive the bond order of the molecule. As the number of electrons present in both the bonding orbitals and anti-bonding orbitals is 2, the bond order is equal to 2 minus 2 divided by 2, which is equal to 0. This proves that a helium molecule is unstable and therefore does not exist. Similarly, beryllium molecule with an electronic configuration of sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and a bond order of 0 is considered to be non-existent. Now let's see the bonding in a lithium molecule. A lithium atom has an electronic configuration of 1s2 2s1. Thus, there are 6 electrons in a lithium molecule. The electronic configuration of a lithium molecule is sigma 1s2, sigma star 1s2, sigma 2s2. This configuration is also written as kk sigma 2s2, where kk represents the closed K-shell structure sigma 1s2, sigma star 1s2. As lithium has 4 electrons in its bonding molecular orbital and 2 electrons in the anti-bonding molecular orbital, the bond order of lithium is calculated to be half of 4 minus 2, which is equal to 1. From the bond order, it is clear that lithium is a stable molecule, and as no unpaired electron is present in its molecular orbitals, it is diamagnetic in nature. This diamagnetic lithium molecule is found to exist in the vapor state. Now, we'll see the bonding in another diatomic molecule, carbon. An atom of carbon has an electronic configuration of 1s2, 2s2, 2p2, which makes a total of 12 electrons in a carbon molecule. The electronic configuration of a carbon molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, which can also be written as kk sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. The bond order of carbon can therefore be calculated as half of 8 minus 4, which equals to 2. In a carbon molecule, the two atoms have a double bond between them. Both the bonds are pi bonds due to the presence of 4 electrons in 2 pi molecular orbitals. A carbon molecule is diamagnetic as no unpaired electron is present in its molecular orbitals. It is found to exist in the vapor phase. Now let's look at the bonding in an oxygen molecule. 2 oxygen atoms combine to form an oxygen molecule. The electronic configuration of an atom of oxygen is 1s2, 2s2, 2p4, and hence there are 16 electrons in a molecule of oxygen. The electronic configuration of oxygen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1, which can also be written as kk sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1. The electronic configuration of oxygen molecule is such that there are 10 electrons in the bonding molecular orbitals and 6 in the anti-bonding molecular orbitals. Thus, the bond order of oxygen can be calculated as half of 10 minus 6, which is equal to 2. Hence, the oxygen atoms in oxygen molecule are held by a double bond. It has been proved experimentally that it is paramagnetic in nature. This is due to the presence of 2 unpaired electrons in its molecular orbitals. Similarly, the electronic configurations of other homonuclear molecules such as boron, nitrogen, fluorine and neon are shown here, from which bond order and magnetic property can be calculated, as given in this table. When hydrogen forms a covalent bond with highly electronegative elements such as nitrogen, oxygen and fluorine, the shared pair of electrons is attracted more towards the electronegative atom. Due to this, hydrogen gains a fractional positive charge, while the more electronegative atom gains a partial negative charge, making the bond polar covalent. When a number of molecules of these compounds are present together The partial positively charged hydrogen atom of one molecule is attracted to the partial negatively charged electronegative atom of another molecule. This weak electrostatic forces of attraction is called a hydrogen bond, which is weaker than a covalent bond. Hydrogen bonds affect the structure and properties of a compound. The strength of hydrogen bonds varies based on the physical state of the compound. For example, in water, each molecule can form 4 hydrogen bonds, giving its viscosity and high boiling point. In ice, the hydrogen bonds create an open, hexagonal lattice crystal structure, reducing the density of ice compared to water at the same temperature. This is why ice floats on water. Hydrogen bond is strongest when the compound is in the solid state, and weakest or absent when it is in the gaseous state. For example, in H2O, the strength of hydrogen bond is more in ice, relatively less in water, and is not observed in steam. The hydrogen bond present in water is said to be an intermolecular bond, which means that the hydrogen bond is formed between 2 different molecules of the same or different compounds. However, in certain compounds like orthonitrophenol, a hydrogen bond is formed between the hydrogen atom of hydroxyl group and highly electronegative atom, that is oxygen of nitro group, present within the same molecule. Such a bond is called an intramolecular hydrogen bond. Thus, we can conclude that a hydrogen bond is the weak electrostatic attractive force between the hydrogen atom and the highly electronegative atom of either the same or different molecule.